Needs a projector, huh? I can see it. Okay. Okay. We are now recording. I recorded that, by the way. Okay, and we'll go from current slide. And let me go over a couple things. I mentioned it before, but in case you weren't here or folks listening at home weren't here, I want to say it again so you'll know for sure. Tuesday, I have a doctor's appointment at 11:40, okay? But I have to be there for blood work at 10:40, which means I have to leave campus here at 10 o'clock. So, no class on Tuesday, okay? None. Zero, zilch, okay, for this class. Now, it's probably going to affect my 12 o'clock class too, but I'll talk with them later. They'll have class, but it will just start a little bit later. Now, I hate that we are missing a class, and I would love to make it up to you. The only time I have that I can make up the class, now, actually for this class, we could do it tomorrow if you wanted to. I could come out here to Bessemer campus, or if Birmingham is more convenient, that we could have the class tomorrow anytime between 7:45 or 11:45, or we can do it either a Monday or Wednesday, anytime from 2 to 6, okay, because I'm on campus. Those are my only office hours I have, more than 10 or 20 minutes at a time, is Monday and Wednesday, 2 to 6. Or we can just not do it, okay? Would you like to make it up? Because I would hate for you to get back to your home campus, because all of you are transfer students, right? And find out, well, you didn't quite cover enough of that, and then they get mad at you and me and everybody at the school here. But if that's not convenient for you, or I could just record the class if no one can come, and you can pick it up. So what would be your pleasure? What would you like to do? Would you like, if I record the class, to be here if possible, or not? Or you just rather I'd not even mess with it, we'll just cover as much as we can? And not try to make this one up? Okay. Well, if y'all are okay with it, I'm okay with that too, because I got plenty to do during my office hours. It's not like I'm sitting on my thumb. So, okay, we just won't try to make it up. I'll try to move along here. So, we will not have class Tuesday, and if the school does something, I don't worry about that. But when I'm the cause of it, I don't want to cheat y'all out of your tuition dollars, okay? So, if you're okay with it, what you think? Everybody is okay? All right. We'll just move as much as we can. All right. Any questions from anything we had up till now? Okay, we did get started in Chapter 1. We finished 1.1, and we're into 1.2. And I have it that we're on page 14, Example 2, the B part. Okay? What we're doing are our elementary row operations. And here is let me get my pen set up. Here is the original matrix. 2, -4. 6, -2. 1, 3, -3, 0. 5, -2, 1, 2. Hope I got them all right. Okay? Now, what if we're going to be doing elementary row operations, what's usually our favorite thing to start with? A 1 in the upper left corner. Okay? In this matrix, you have 2 possibilities to make that happen. Do you see them? You could swap row 1 and row 2. That's a legitimate elementary row operation. Or row 1 plus the negative of row 2. All right. I guess you could do that, and that's legal. Okay, that is another elementary row operation that you could do. but one that's a little simpler than that. Divide the first row by 2. That's probably actually easier than the other because you don't have to mess with 2 rows, just 1. So, but any of those would work, but the one they're illustrating now is row 1 divided by 2. Okay? And here's Lauren's back. Okay? This happened in my first class too. At some point we had the middle of the alphabet missing the top and missing the bottom, okay? And as it turned out in my first class, the top came in, so we had everybody but the bottom. That's what we'll get them both in today, or at least get the top. But I'm glad y'all are here. Okay. The one that was 6 people in this one. And 7 people in the other one. So, actually, together, these 2 classes might count as 1 class for me, so I might wind up getting paid a little bit for this. Okay, don't know for sure, but I know you are worried about that. But you can rest your minds now. You feel comfortable. Okay, so we're going to divide the first row by 2, and what does that give us? And then you just copy the others down. 1, 3, negative 3, 0, and 5, negative 2, 1, 2. Okay? And then you proceed with the others. Okay? And I think you can see some easy steps to do that. That's all they wanted you to do on that. Okay? Now the C part. Okay? Here's the original matrix. 1, 2, negative 4, 3. 4. It's ugly, but it's a 4. 0, 3, negative 2, negative 1, and 2, 1, 5, negative 2. And sometimes I don't quite get things lined up well. Okay, what elementary row operation would be your choice of what to do first? First, what do we want to have? 1 in the upper left. We got it. Ching-ching. Okay. What do you want after that? A 0 below it. We've got that. Cha-ching. Okay, next. 0 below that. How do we make that happen? Second?
You take row 3.
Okay.
Subtract 2 times the first row.
Okay, all right. And how they usually write it, but what you said is absolutely right. Minus 2 times row 1 plus row 3. Now, you said it the other way. Row 3 minus twice row 1. Perfectly fine. And if that's how you like to think of it, do it. I'm just saying, here's how the book, oh no, they didn't. I'm sorry. They wrote it exactly like you said it. Row 3 minus 2, row 1 is a new row 3. They put that other part in. Okay, so what does that give you? Since you're using row 1, don't change anything. Write it down. 1, 2, negative 4, 3. That times the negative 4 looks better. You're not doing a thing to the second row, so write it down. 0, 3, negative 2, negative 1. This is what makes linear algebra sort of long and tedious, is that you got a lot of copying and just writing things down. But let's do the new row 3. What does it become? 0, negative 3, second, 13. Okay. Negative 8. Perfect. Okay, way to go. Now, that's all they're looking for here. Sometimes I break from what the actual rules are, or how they want you to do things, and in the order they do. When I see one like this, my next step is wanting to add this to that and make that a 0. Okay? Even though they most of the time are going to want you to make that a 1 first. This is so easy to do that. To make this a 1, you have to divide by 3. That gives your fraction here, and then you're multiplying and adding fractions. And I tend to make errors when I do that. If I just add these two, I can do that pretty easily without making too many errors, maybe. Okay. So take advantage of little instances like that. Just like you were going to, if you saw it better, subtract row 2 from row 2 from row 1 and make it the new row 1. And those are okay to do. It doesn't really fit their jive, but if you're all right with it, as long as it's a legal move, you can do it. All right, so that ends example 2. Any questions on that? Let's go to example 3. Okay, well, before we do, well, I can go to it. We don't need to. The paragraph before example 3 says, in example 7 back in 1.1, we used Gaussian elimination. Remember what that was? You're trying to get what we've just been describing. 1 is the first non-zero entry in the top row, upper left if possible. 0 is below it. So go to the second row, first non-zero entry of 1, 0 is below that, and on down like that. So you have zeros in the lower quadrant, you might say, or portion of your curve. So that's what we were doing with linear equations. This next example demonstrates that same type of operations, getting Gaussian elimination with a matrix. And that's what we were gunning for. The two methods are essentially the same. The basic difference is that with matrices, you do not need to keep writing the variables. So that's what the matrix does for you. So here's a linear system. X minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17. Okay? Now, again, let me emphasize this. They're giving you these perfect form here. If you happen to be, like in the real world out there, and you have this bunches of equations, they have to be, all these conditions have to be met at the same time. That's what the system of equations tell you. Then you write them down, but here's the key. Be sure you put variable over variable, equal sign over equal sign, constant over constant. Be sure you have it in the standard form before you start trying to mess with it. If you wrote minus x plus 3y is equal to negative 4, and then you wrote down the matrix for this, and you happen to put the negative 4 in here, no, don't do that. Be sure you do. And so it's a good idea to get things in order, very specific, then do your matrix. They gave it to you this way, so it's good. So let's produce the augmented matrix that system of equations corresponds. What would it be? 1, negative 2, 3, 9. Negative 1, 3, 0, negative 4. 2, negative 5, 5, 17. And if you recognize that, this is the system of equation we did before. Before we did it as equations, now we just do it with the matrix. And we're doing the same thing. What do we want to happen to that matrix first? 1 in the upper left corner. We got it. Okay? Done. What do you want to happen next? 0 below it. How do we make that happen? Second? Yeah, row 2 plus row 1. Either way you want to say it. I think the book usually says, nope, they said it just that way. So row 2 plus row 1. Okay? I've taught from other books, as in my, I think well, actually, we don't use that book anymore. when we did our finite math does this kind of stuff too, and that the book we were using back then always had those reversed, so I've just gotten in the habit of doing that. Okay, so you are using row 1, write it down. Don't change a thing in row 1. That's like you want it, at least so far. Okay, you're changing row 2, what does it become? 0, 1, 3, 5. And you didn't do any, well, okay, now, to keep from having to write so many stinking things, let's go on and operate on row 3 without copying row 3 again and then copying row 1 and 2 again. Let's just be smart about it. What's the next thing we're going to do? Okay, say that one more time. Row 3 plus, isn't that a, oh, you did row 2. Okay. You know, that is a legal move. That's not the one they had in mind, but it is. Or you could do minus row 1, minus 2 row 1. That's what they usually do, but let's do it your way and see if it should give the same answer. And you said plus 2 row 2, okay? The original row 2, not the new row 2, okay? That's the only thing you have to keep in mind now, okay? So let's do it your way. And what does that give you? 0, 1, 5. Okay. Yeah, 9. Okay? Okay. We're deviating from what the book does, but that's okay. We're going to see if it comes out the same. Okay, what do we want next? Once we have a 1 in the upper left and 0 below it, what's the next thing we want? The first non-zero entry in row 2 to be a 1. Hey, we got it already. Okay? And what do you want to happen next? 0 below it. How do we make that happen? Row 3 minus row 2 should do it. So row 3 minus row 2 will be our new row 3. So we got a 1, negative 2, 3, 9. Leave that one alone. We're using row 2, so it's 0, 1, 3, 5. But what's our new row 3? 0, 0, 2, 4. Okay? Now, what's the next thing we want to happen? We have a 1 in the upper left, 0 is below it. First non-zero entry in the second row is 1, 0 is below it. What's the next thing that happen? First non-zero entry in row 3 to be a 1. And how do we make that happen? Divide by 2. Okay? So row 3 divided by 2 is the new row 3. And that's going to produce 1, negative 2, 3, 9, 0, 1, 3, 5, and 0, 0, what? 1, 2. Okay, now we begin the back substitution. What does that third column represent? The coefficients of z. So you have z is equal to 2. All right. Z is equal to 2. Okay? Then what do we do with that? Go up to row 2 and back substitute that into the next one. Well, the next one says y plus 3z is equal to 5. That would be y plus 3 times 2, that's what z is equal to 5. Solve that for y, and what do you get? Y plus 6 is equal to 5. Y is equal to negative 1. Okay. What does the first row tell you? Okay, yeah, plug in that. So I'm going to write it out. After a while, you don't have to, but I just want everyone to see it. X minus 2y plus 3z is equal to 9, which was really your first equation always. And that now becomes x minus 2 times a negative 1 plus 3 times a 2, and that's equal to 9. I'm running out of room. Okay. So that makes x equal, if I can do this, 9, and this would be a plus 2 on this side, making it a minus 2 when you pull it over. And that's a plus 6 now, so that becomes a minus 6. So that would be x equal 1. So 1, negative 1, 2 is our solution. And if you'll go back and check in section 1.1, that's the same thing we got there. Now, we have a special name for this in matrices. Before, it's just called Gaussian elimination with back substitution. And that's what you're doing, but what form we wind up with here, and here's the keys for it. The leading non-zero entry in each row is a 1, okay? And they stair-step to the left, to the right, going down, okay? That is called row echelon form. I don't know what echelon means, but that's what the term is. This form is called row echelon. I'll make sure I spell it right. E-C-H-E-L-O-N. Never use the term anywhere but in this course or something that's teaching matrix. Row echelon form. Again, let me say the properties. I'm going to have to erase this because I can't write it all on the page. You okay with it? Okay. So, row echelon form has the following properties. Any rows consisting entirely of zeros occur at the bottom of the matrix. I can't write. Any rows with all zeros, all zero entries, are at the bottom. And that can happen, okay? So that's the first. We didn't mention that before because our other didn't have zero rows, okay? But the rest of them we've said before. For each row that does not consist entirely of zeros, the first non-zero entry is a 1. For rows not all zero, first non-zero entry is a 1. Okay? That's called the leading ones, by the way. We'll use that term a lot. The third thing is, for 2 consecutive non-zero rows, okay, the leading one in the higher row is further to the left than the leading row in the lower row. Leading one in the lower row. Okay. Or the other way you could say that the leading one in the lower rows is to the right, always to the right of the leading one in the upper row. I wrote it the way the book did. I usually think of it the other way. Now, that's row echelon form. There's one additional thing they mention here that we haven't done yet, and that is a matrix in row echelon form can be put into reduced row echelon form by few more steps, but it's pretty simple. When every column that has a leading 1 in it, not only do you have zeros below it, but you have zeros above it. You just reverse the process and go up. When every column that has a leading 1 has zeros in every position above and below the leading 1. So for reduced row echelon form, the leading ones have zeros above and below. I can't write. Okay. So you just continue the process and put. Now, what's the advantage of reduced row echelon form? And that last one, if we had taken it the next step, what we had at the end was x equal, what was it, 1, y equal -1, or whatever the answers were, you just have them right there. You don't have to do back substitution. So, pay your money and take your choice. You've already paid your money, whichever one you prefer. It's pretty easy to get it in reduced row echelon form. It's usually just a few more steps, and back substitution, especially in a big matrix, can be pretty hairy sometimes. So you might want, that's what reduced row echelon form is. It's not red, it's reduced. Okay, now example 4 is a pretty simple example. It's determine whether each matrix is in row echelon form, and then if it is it in reduced row echelon form? Okay, so here's A. We're not doing anything to them, we're just answering the question. 1, 2, -1, 4. 0, 1, 0, 3. 0, 0, 1, -2. First question, is that in row echelon form? Yes. Your leading entry in each row is a 1. The leading non-zero entry in each row is a 1, and the 1s move to the right as you go down. Okay? That's what's required. Is it in reduced row echelon form? No. The second one, leading 1 in the second row, has a 2 above it, and would need to have a 0. The third leading 1 has a 0 above it, but it would need a -1, the -1 to be a 0 as well. So it's not reduced row echelon form. Okay, here's B. 1, 2, -1, 2. That looks pretty, oh no, it's not quite the same. Okay, 0, 0, 0, 0. And 0, 1, 2, -4. Is that in row echelon form? Help me out. No, why not?
Because 1 is not leading on row 2.
Say that again.
You don't have a 1 on row 2.
Okay. Now that's one way of expressing it. Here's the way the book said it. Any row of all zeros has to be at the bottom. Okay? That's what to do. So to make that in row echelon form, just exchange rows 2 and 3. Then it would be in row echelon form. You're right. The second row doesn't have any leading 1 in it, but it doesn't have to. But if it were, then all the rows below it couldn't have any leading 1s either. And this one does, so you reverse those 2, then you have it in row echelon form. Is this in reduced row echelon form? No, if it's not in row echelon form, it can't possibly be in reduced row echelon form. Okay, good deal. Number C. Okay? Let's Yes, in Spanish, by the way. Okay. 1, -5, 2, -1, 3. 0, 0, 1, 3, -2, 0, 0, 0, 1, 4, and 0, 0, 0, 0, 1. Is that in row echelon form? Yes, it is. The fact that the third row doesn't have a 1 in the third column, or I'm sorry, the second row doesn't have it in the second column, that's immaterial. It's just the first non-zero entry in every row is a 1, and they step down, and there are no rows of all zeros. So yes, that's row echelon form. Is it reduced row echelon form? No. Okay. It would be, you would have to have a 0 there, and all of those. It would be reduced row echelon form. So it's not. Okay. Even though it is row echelon form. Now, could this be an augmented matrix of 4 equations, 4 unknowns? You say yes or no? No, why not?
Because for the last one you have 4 unknowns that all make their difference of 0 equal to 1.
Right. And if that were, this would be inconsistent system. No solutions because of that very reason. Okay? If all these did represent variables, and 0 can't equal 1, so it would be an inconsistent system. It could represent 1, but it would be an inconsistent system. It wouldn't be a consistent system, one that you have a solution to. Okay. Now, back up again. What if that was a 0 here? Okay? That would be a consistent system if that could, but you would have a parameter in here for your variable 2, whatever your second variable, x of 2, whatever that was, that would be a parametric because you don't have a leading 1 there. So it would have a parametric thing, so you would have an infinite number of solutions there. But this doesn't necessarily represent systems of equations. If it did, then those would be conditions, but it doesn't necessarily. It doesn't have to. Okay, here's D. 0, no, I'm sorry, I can't write. I can't read. Okay, 1, 0, 0, minus 1. 0, 1, 0, 2. 0, 0, 1, 3, and 0, 0, 0, 0. Okay. Is this in row echelon form? Yes, it is. Is it in reduced row echelon form? Yes, it is, because every leading 1 has zeros above and below it, except for the first one. Okay. Now, could this represent a system of equations? If it could, since you only have 4 here in the left column are your constants, this would be 3 unknowns with 4 equations. Well, that fourth equation was obviously extraneous. So 3 equations of 3 unknowns, we know exactly what they are. C is equal to 3, y is equal to 2, x is equal to -1. That's the beauty of reduced row echelon form. Whatever the fourth equation was, it was dependent on the top 3. So when you did your row reduction, you wound up with all 0. Okay? And that could be the case, but it's a perfectly good system. Okay. Make sense? Now, I think I'm going to have to go to a... Sorry, I've got the yawns now. I don't know why. I think I do know why. I didn't drink enough water between class and I'm getting a little dehydrated. I'm sorry. I ate a stick of string cheese and that was salty, and I think that's what's making me a little nuts here. Okay, here we have a 1, 2, -3, 4, a 0, 2, 1, -1, a 0, 0, 1, -3. Is that in row echelon form? Okay, I see a no and a yes. Defend yourself. Why isn't it? All right, yeah, you convinced them. Okay, what keeps it from being row echelon form? That 2, okay? The leading entry, non-zero entry in each row must be a 1. That has a 2, so that's not. It's easy enough to make it row echelon form. How? Divide the second row by 2. So that would be 0, 1, 1/2, -1/2. I admit that's a lot messier, but that would be in row echelon form. Okay. And that could represent a system of equations. Yeah. Let's do F. 0, 1, 0, 5. 0, 0, 1, 3. And 0, 0, 0, 0. Is that in row echelon form? Second? Yes, it is. Absolutely is. Now, what it doesn't have is that upper left corner being 1. But guess what? It's not required to be. Now, I can't imagine a system of equations that would be the case, okay? Because usually if you have 3 variables, you have a coefficient there. But this doesn't. But that doesn't have to be representing equations. That could just be a matrix. That matrix is in row echelon form. Okay? Good deal. Is it in reduced row echelon form? Okay, yeah. Actually, by the definition, all it required is that the leading ones have zeros above and below. If you only have 2 leading ones, that have zeros above and below. So yes, technically it is in reduced row echelon form as well. Now let me see if okay, the matrices, and we don't have them all up there now. A, C, D, and F are all in row echelon form. That's what we agreed with. The matrices D and F are in reduced row. Yeah, we got them. Okay. Now, sorry. Every matrix in row equivalent is, okay, sorry, got the verb wrong. Every matrix is row equivalent to a matrix in row echelon form. Okay? Get that again? Every matrix is row equivalent to a matrix in row echelon form. You can always get it to row echelon form by using those 3 steps, legal maneuvers in to produce equivalent matrices. For example, in 4C, and we already said this one, you divide the second row. We don't have it up. Oh, no, there it is, right there. Not CE. Divide the second row by 1, and you can get it in row echelon form. Okay. So the following summarizes the procedure for using Gauss elimination with back substitution. Boy, we've already done this, and I don't know. Actually, well, I guess we haven't written these steps down, so I'll write them down. I think I've got room to do them here. This is Gaussian elimination. Is that right? Yep. Doesn't look right with two S's in it, but it is. Elimination with back substitution. Okay. 1. Okay. Write the augmented matrix of a system of linear equations. Okay. Yeah. So, Gaussian elimination with back substitution. First thing, you have the system of equations. Write this augmented matrix. Okay? That's it. Just write the augmented matrix. But be sure you line up variable with variable, equal sign with equal sign, constants with constants. Make sure everything is lined up that way before you write it, or when you write it. Make sure you don't have anything out of line. Okay? Number 2, use elementary row operations. Now, here is my abbreviation, elementary row operations, okay, ERO. Elementary row operations to rewrite the matrix in row echelon form. Okay, and again, I'm going to start calling this RE form. RE is row echelon form. Okay? Number 3. Write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. That's what I was doing. I don't want to write all that down. So I'm going to just rewrite the system of equations. And back substitute. I can't write. Whatever, okay. My eyes are getting so dry, I don't know. We've had so much rain, I think I've got used to all the moisture. Now the AC is taking it out. Okay. So Gaussian elimination with back substitution works well for solving systems of linear equations by hand or with a computer. It's not that hard to, depends on how your programming skills are, to write programs that do this. It's very regular. Okay? Now, the little tricks you like to do by subtracting in different order out of thing, computers don't like those, okay? You have to be very orderly and do the same steps every time with the computer, okay, when you're writing code for the computer. You can't look at it and say, oh, it would be so much easier if we did it this way. Computers don't do that. They grind through, however, okay. For this algorithm, the order in which you perform the elementary row operations is important. Operate from left to right by columns using elementary row operations to obtain zeros in all entries directly beneath the leading ones. Okay. Now, quite often, not always, but quite often in a section when you get to the end or somewhere in the section, it'll have a little blurb on linear algebra applied. And I may have mentioned this, I think I did early on. Have you ever wondered how your phone can tell you where you are, and which way to turn, and all that kind of stuff? Using GPS. GPS uses at least 3, I'm guessing probably more than 3, but no fewer than 3 signals from various satellites. If you don't have 3, there's no way you can get it to work. But if you have 3 signals from 3 satellites above you, relatively spaced apart, they can't be in line with each other, they have to be spaced apart, then that's a linear algebra problem. That's what your computers are doing. Figuring out what your position is based on that. So GPS is a network of 24 satellites, okay? Originally developed by the U.S. military as a navigational tool, but now they can be used by civilians as well. Okay, you need at least 3 signals from at least 4 satellites to trilaterate. Okay, you need 3 to triangulate, but to get trilaterate, I think that accounts for differences in elevation too. That's why you have to have the 4th. To get position on the globe, you need 3. And guess what? I was in the Navy, and I was actually on board a ship when we got the first, and what we called that then was SAT-NAV. Of course, everything's abbreviated in the military. Satellite navigation, okay? And we received our antenna, new SAT-NAV antenna, and we were just learning the system, and then we were going to go into the yards for a year, and we were doing a test on the the manual anchor windlass brake, and it failed, and the bitter end of the anchor chain came flying up and tore up our brand new satellite antenna, not the satellite, but the antenna, and the captain was not too happy. But I was sort of thankful for the antenna being there, because I was on the forecastle, that part of my job was to oversee all this, and we were yelling, stop, stop, but we couldn't get the brake to hold. And when that bitter end came out, I mean, it was a huge chunk of steel, several tons, came flying out of the hose pipe below, and going down, it went whop, 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 whop on the way down. And that first whop left serving bowl indentation in a 5-inch steel thick deck about 18 inches from where my foot was. And I just wonder if that satellite antenna was just enough to deflect it so it didn't, my steel toe shoe wouldn't have made any difference at all. I would have been footless if not completely wiped out. So I think fondly of satellite antennas. Never mind. Okay. I'm sorry. The 4th unknown would be time. I'm sorry. It's not elevation, it's time. I haven't read far enough. If that's of interest to you, that may be a potential paper topic. This is not your only source. You have to get some sources outside the book. This can give you an idea of what you might want to write your paper on. All right, let's do example 5. Here's a system of equations. X sub 2 plus x sub 3 minus 2x sub 4 is equal to negative 3. X sub 1 plus 2x sub 2 minus x sub 3 is equal to 2. 2x sub 1 plus 4x sub 2 plus x sub 3 minus 3x sub 4 is equal to negative 2. And x sub 1 minus 4x sub 2 minus 7x sub 3 minus x sub 4 is equal to negative 19. All right. Goodness, my eyes are dry. I think the other thing is writing over this, the heat from the fan blows right up into my face, so that's probably another reason for that. All right. what's your first step? It says solve that system. Anyone want to do graphing? Not me. Okay. Second, augmented matrix. Good idea. I like that concept. So what would that augmented matrix look like? 0. Yuck. For some reason the pen's not writing. Next. 1. 1. -2. -3. Next. 1. 2. -1. 0. 2. Next. 2. 4. 1. -3. -2. Next. 1. -4. -7. -1. -19. Okay, good deal. Next, what's next? Next step. Have either one of two good choices. Have another possible third choice. What would you do? Okay, you want to flip the top 2 rows? Is that what you said? I don't hear well.
You could either flip the top 2 or the top 1 rows.
Yes, exactly. That's my 2 good choices. Do you have a preference? Since they're close, let's just do the top 2, okay? So row 1 and row 2 interchange. Okay, that's my symbology. Double arrow. Okay. So now we have 1, 2, -1, 0, 2. 0, 1, 1, -2, -3. 2, 4. See, the other option was divide third row by 2 and then flip them. But that would have involved fractions. I avoid those if I can. Okay. What's that?
You already have a 0 on the second row.
On the...
Your second row
Yeah.
has a 0, so that's better than having the 0.
Right. Yeah, I agree. I thought you were talking about what I was saying. Okay. That'll be -3, -2, right? Okay, and the fourth one is 1, -4, -7, -1, -19. Wow, I didn't realize there were so many negatives in that one. I hope I wrote it right. Okay, so there we have next step. Next, what you want to happen.
To get another 0 below that.
Okay, where the 2 is? Yeah, okay. I agree. So what are we going to do to get it there? Row 3 or -2 row 1. Yep. That'll be our new row 3, right? Okay, so let's write down the first 2 rows. 1, 2, -1, 0, 2. Like I said, linear algebra is a lot of copying, okay? 0, 1, 1, -2, -3. I hope I got that right. Okay? Okay? And what's our new row 3 then? 0. Oh! You're right, 0. Three. Is that what I heard? Okay, right. Okay. -3.
So that row should be -3, -2 as from the first matrix.
Okay. Oh, did I write something wrong?
Coming down -2 should be -3.
Oh, that's a -3 there. You're right. Is that the only? Whoops. Okay. That's the only error I make. Okay. Okay, what you got then? -3. Got it. Okay. -6. What is that? Yeah, -6. Okay. Next. Say again. No, I don't think so. What do we want it to be? We want it to be at 0. Okay, yeah. I don't do this and then do it again. Let's only take care of this one. We took care of this one. Let's do this one next. So what do we want that to be? 0. How do we make that happen? Okay, yeah. Row 4 minus row 1. Row 4 minus row 1. Okay, and what will that be? 0. -6. -6 again, is that what you said? Okay. -1. And -21. Ew. Not getting very pretty there, is it? Okay. And what do we want to happen next? You got a 1 here, 0 is below. And now what?
Row 4 plus
Okay.
6.
You got the 1 here, you got 1 0 below it, you need that. So what are we going to do?
Row 4 plus 6 and row 2.
Okay. Row 4 plus 6, row 2. Perfect. Okay, we're not using row 1, so write it down. 1, 2, -1, 0, 2. We're not using row 2, well, we're using row 2, but not changing it, so that's 0, 1, 1, -2, -3, if I copied it right. Okay? Now, do you mind if I do this now, just to keep from writing it again? What do you notice about row 3? Yes, so let's do row 3 divided by 3, so we don't have to write all those things down again. I'm lazy. Okay. Have I told you all this now? This is just sort of a theory or principle that I've developed over time. I think to be really good in math, you have to be a little bit lazy. Okay? Do any of you qualify? No. Okay, we got one budding mathematician here. Okay, good. And why do I say that? Because you're always looking for the easiest way to do a problem. That's what makes you pretty good at math, I think. Now, hard workers can still do it, so don't discount yourself. You can still do it, but it just makes it easier if you're a little lazy, I think. Okay, so let's go on and do that. 0, 0, 1, -1, second, -2, right? Okay, good. I can't hear well. All right, now we're going to do what we said before. Okay, row 4 plus 6 row 2. So what do we get here? First entry, 0. Next entry, 0. Next entry, really? Row 4, that's a -1, plus 6 times, second?
Are you on the third column?
Third column, right.
So -6 plus 6.
Oh, I'm sorry, I had gone to the next one, okay. Yeah, you're right. So that's -6 plus 6, that's a 0, yeah. Wow, nice. Next? Yeah, I was on the fourth one, sorry. -13. Next. Okay, yeah, negative 39. Okay, that would be a negative 21 minus 18. Yeah, negative 39. Sounds pretty rotten until you look at the negative 13 and say it's not going to be too bad. Okay, what do we want to happen next? Okay, let's rehash a little bit. You got 1 here, 0 below. 1 here, you wind up with 0 below there. Not bad. Then you have a 1 here, 0 below that. We took care of that one. What do you want to say? Okay. We want to take row 4 and do what to it? By negative 13. And that will do it for us. Can I just do it right there? Since I don't have room to write it underneath. So this will be a what? A 1. And that will be a 3. All right. I did it. Okay. Now, we've got it in what form? Row echelon form. So now we can do our back substitution. We could do reducing if you wanted to, but it said do it with back substitution. So we'll do what they say. So what's the first thing I can write down? I have to go back and check what my variable was. X4 is equal to 3. Okay? Now, I'm going to try to speed things along a little bit by doing it this way. X3, okay, is equal to your constant, which is minus 2, and then I'm going to move the X4 to the other side, so that makes it a plus 3. You see what I did there? I just don't have much room, so I'm being lazy again. Okay? Here it gives you X4 is equal to 3. This gives you X3 is equal to negative 2 plus X4, right? Would you rather not do this? Okay. Let's go back. All right. Never mind. Okay. Just take it from scratch. Okay? The third row says X3 minus X4 is equal to negative 2. Agreed? Okay. Plug in what X4 is. It'd be X3 minus X4 is 3 is equal to negative 2. And then add 3 to both sides. And that gives you X3 is equal to 1. Right? All right. You tell me what to write next. What does the second row tell us? X2. Second. Okay, y'all okay with that, or you rather write it? Okay, you're okay with it. Okay, so that's equal to negative 3 minus X3, which is 1, right? Plus 2 times 3, which I said 2 times 3 and wrote 6. My pen got ahead of my brain or whatever. Okay, so that would be negative 4 plus 6 was 2, right? All right, and then let's get to X1. And what could you write there? Equal to what? 2 minus 2 times 2 is minus 4, right? Plus X3, which is 1. X4 is 0. That should do it for us, shouldn't it? And that would be -1. All right. So our answer is an ordered 4-tuple, whatever you call that, okay? And that would be -1, 2, 1, 3. Okay. X1 equal, okay. Let's see what they got. X1 equal -1, yes. X2 equal 2, yes. X3 equal 1, yes. And X4 equal 3. Yes, 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 yes. All right. Any questions? Good deal. Y'all will catch on to this quickly. Have y'all had it before? You sound like you didn't have. No? Y'all are good. Okay. All right, let's move on to example 6. All right. Here's a system. X1 minus X2 plus 2X3 is equal to 4. X1 plus X3 is equal to 6. 2X1 minus 3X2 plus 5X3 is equal to 4. 3X1 plus 2X2 minus X3 is equal to 1. First step. Do an augmented matrix. And what would that be? Great. What's the first thing you want to have happen? You already got it. Upper left is a 1. Good. I love it. Next. Delete 0 below that. So what are we going to do to make that happen? Well, first, since we're using the first row, it was just like you wanted it. 1 minus 1, 2, 4. Leave that alone. Now what? Row 2 minus row 1. Okay, and what would that give you? 0, 1, -1, 2. Perfect. What you want to happen next? 0 where the 2 is. So how would you make that happen? Row 3 minus 2, row 1. Is that what you said? Okay. All right. And what would that give us? 0. Yeah. I got lost. Okay. Okay, I've got to find myself again. Yeah. -4. Okay? What you want to happen next? 0 below that. And how would you make that happen? Okay, row 4 minus 3, row 1, and what would that give you? 0. Yep. -7, you said? Okay. -11. All right. Now, what do you want to happen next? Okay, you want the first non-zero entry in row 2 to be a 1 and it there already. Okay, and then what next you said? You want a 0 below it. And that's going to be really easy to do. How? Yeah, perfect. Row 3 plus row 2. Okay? Let's see, I'm going to write it down here. Okay? So leave row 1 alone. 1 minus 1, 2, and 4. Okay, leave row 2 alone. 0, 1 minus 1, 2. And now what's your new row 3? 0, 0, 0, -2. What do you want to happen next? You already know. What? Is what? Inconsistent. Can't happen. This means that 0x1 plus 0x2 plus 0x3 is equal to -2. Not in this universe. Okay? Can't happen. Stop right there. Stop the presses. Inconsistent system. The whole system doesn't work. Don't need to go any further. Inconsistent system. Okay? Now, yeah. They got that far. They did the 4th row, no reason to. Okay? Because 0 cannot equal -2. Just not possible. So stop right there. All right, any questions on that? All right. Now, just a little bit of background here. With Gaussian elimination, you apply elementary row operations to matrices to obtain a row equivalent row echelon form. Second method of elimination, called Gauss-Jordan elimination, basically does reduced row echelon form. Okay? Now the Gauss is from Carl Friedrich Gauss, we mentioned before. If I'm not mistaken, was he German or Swiss? I know we had him in here. I want to say German. Yeah, German mathematician, Carl Friedrich Gauss. Okay? Now he's joined by Wilhelm Jordan. Now that sounds pretty German to me too, but not really. I said joined by or whatever. You might say augmented by, because Gauss lived 1777 to 1855, and that means Jordan was 13 years old. No, 15 years old when Gauss died. So I don't think they really colluded any together. Jordan just picked up where Gauss had left off. And Jordan continued the reduction process until a reduced row echelon form was obtained, and that's produced the Gauss-Jordan elimination. So Gauss elimination, row echelon form, Gauss-Jordan elimination, reduced row echelon form. Okay? So let's now, I was going to say, did they give us the same system of equations? No, they didn't. Shame on them. But I think it's one we had before. But let's deal with it. Okay. Here's the system of equation. X minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to -4. 2x minus 5y plus 5z is equal to 17. I've been making all other kinds of excuses, but I'll let you know this for future reference. Usually by Thursday, I'm getting white slick. Okay, so one of the side effects of the treatments I've been taking, it knocked the white blood cells down just like it was supposed to. I mean, it's wiped them slick. I'll find out Tuesday how well, but all the early indications are it's done a great job. The bad news is it's also destroyed a few of the red blood cells, so I'm very anemic. And so by the end of the week, fatigue, just total fatigue. So excuse my yawning. That's just part of the deal here. Okay. Have I written these down? Yes, I think we've finished. All right. First step. Help me out. I'm too tired to do all the work. Write the matrix. And what would it be? 1, -2, 3, 9, 0. Say? -4. Perfect. I can't hear, so sorry. 2, -5, 5, 17. I think I've seen this one before, haven't I? Okay. What do we want to happen first? Already there. 1 in the upper left. Fantastic. We love to see it. And then what? 0 below it. Okay, so what are we going to do to make that happen? Let's just write down the first row. 1, -2, 3, 9. Okay, how do we get a 0 below it? Row 1 plus row 2. It doesn't matter which order you do it, but the book usually does it the other way, but it's fine. So what does that give us? 0, 1, 3, 5. Okay, what do we want to happen next? Yes, it is. And how do you make that happen? Second?
Multiply the first row by
-2 and add it to the third. Very good. So I'll do it the way Evan does it. Row 3 minus 2, row 1. You can say -2 row 1 plus row 3. That works too. Okay? It's a little shorter to do it this way because you don't have the foot. Right. Okay. So what would that give us? 0. Okay. So -5. Yeah, -1. Perfect. Okay. I got lost. Okay. Next. -1. Okay, you got it. -1. That'd be a 17 minus 18 is -1. Perfect. Okay. What do you want to happen next? To be a 0. Okay. But you also want the -2 above that leading one because we're doing reduced row echelon form, Gauss-Jordan elimination. So you also want that -2 to be a 0, the one above that one. And this time we're going to do both ways. So since we're going to start with that, I don't want to write that one again. I want to change it first. So what would we do to get that -2 to become a 0? Yeah, well, it's the same as we did before. We're using the leading ones, that's what we call them, the leading one, to make the changes. So we'll do twice row 2, add to row 1. See, just as if that -2 had been below it, that's what you do, right? So with above it, you did the same thing. So let's do twice row 2 plus row 1, or whichever way you want to do it. Row 1 minus 2, plus 2 row 2. Either way you want to do it. So I don't think I have room to write it there, so let's write it here. And what would that be? 2 times 0 plus 1 is? One. That's exactly what you want. You don't ever want to change that 1. You want that leading one just like it is, but since you got zeros below it, you can multiply by anything you want to. Add it to it. It's going to stay a 1. Okay, next. Zero. Next. Really? Second. I may have written something down wrong, but 9, okay, and 19. Ew, this isn't looking too good, is it? Okay, next, we're using row 2, so leave that alone. 0, 1, 3, 5, okay? Now, what do we want to happen underneath that 1? You want that to be a 0, so how do we make that happen? Second? Row 2 plus row 3, right? All right, and what does that become? 0. Whoa, what is it doing here? I don't know what it's doing. It's messing up. Okay, I got it back. But it went back to the red. This is nuts. Okay, so that's a 0. And by the way, I slashed my zeros if you haven't figured that out yet. Next. 0. Next. 2. Next. 4. That was easy, wasn't it? And what do we want to happen next? Let's recap. You have a 1 here, 0 is below it. You have a 1 here, 0 is above and below it. This is reduced row echelon form. Gauss-Jordan elimination. So what's the next thing you want? A 1 here. How do we make that happen? Oh, yeah. No, okay, now there you don't want to do that. Because you see, if you did that and that becomes your new row 3, that makes that a 1, and you don't want to go backwards. So at this point, it's usually good to follow the pattern. And what do we want to do? Divide by 2. Okay. Now, just to save a step, can I just erase it? So row 3 divided by 2. And let me just do that, and that would make the this a 1. Okay. And make the 4a 2. Okay. You probably should write it out. I just am really lazy. What do we want to happen next? I should have written, yeah, well, okay. What do we want next? Zeros above, both at the 9 and the 3 place. So what are we going to do on row 1 to make that happen? Row 1 minus 9 row 3. Okay, let's make that happen. Okay, the row 3 is going to be 0, 0, 1, 2. I could have waited and written it there. In fact, I think I'll do that. Let me go back just so your notes. Yeah. That was a 2, 4. Okay. So, doesn't matter. Okay. So, do what I said. What you said. 1. 0. Notice those things don't change. You don't want them to change. Okay. Next. 0. Very good. Okay, trying to read my writing here. That's a 9. Oh, 19. Okay, that's where I was reading a 9. 19 minus. Okay, I'm going to change this back, okay, because I'm getting myself confused here. Okay, make that a 1, 2. Okay, yeah. Okay, now let's do it. That was a 0, and that would be a 19 minus 18. So that's a 1. That's what you said, right? Next. Row 2 minus 3, row 3. Okay, and that would give you a 0, 1, 0, negative 1. And what does this give you? Boy, I like this step. Row 1 tells you x equal 1. Row 2 tells you y equal negative 1. And row 3 tells you, ooh, isn't that nice? No back substitution. It was just a little more work to do reduced row echelon form, but then it makes it so much nicer at the end. Okay? So, like I said, pay your money, take your choice. And this is exactly what we got: 1, negative 1, and 2. Okay? Now, they have a little blurb here, statement. The elimination procedures described in this section sometimes result in fractional coefficients. No way around them. They've been very, very nice to us so far by giving us integral coefficients. That's not always the case. Don't bank on it, okay? Sometimes judiciously choosing the order in which you apply the elementary row operations enable you to at least minimize the fractions. So let's take a look at the one they have here. I don't think they even give you an answer, but I want to write it down anyway. Okay. All right. I thought I erased that. Why is it not erasing? Okay, something is wrong with something. I don't know what it is. That. No. Well, I know something that'll work. Well, I thought it would. I hate to do this, but I think I've got to. It takes a while. I don't know why it wouldn't erase anymore. I must have done something that it didn't like. Okay. Okay, we're back. 2x. No, I've got to change my color back. Okay. 2x minus 5y plus 5z is equal to 17. That's the last equation from the previous one. I don't know why they're using it again, but whatever. 3x minus 2y plus 3z and that's equal to 11, and minus 3x plus 3y is equal to negative 16. Now, let's not write it all down, but at least talk through it. What would be your first step? Huh?
Matrix.
Yeah, right as the matrix. Okay, let's just imagine it. What we'll do is just take out the x's, the y's, the z's, and the equal signs. And you got it, right? I can do that, actually. Is it all right to do that? You probably have more trouble doing it on yours than, okay? There, I did it, okay? And hopefully it came out right. Okay. Okay. Now, what would be the next thing? What's the first thing you want? A 1 in the upper left, and it's not there. How could you make it happen? Second? Okay, good idea. Subtract row 1 from row 2. Is that what you meant? Okay. So in other words, row 1 minus row 2. No, row 2 minus row 1. Now, you would have to make that your top row 2, and I think that's okay to do. And that would eliminate introducing fractions. See, if you divide it by 2, then you get a 1 there, but then you get a minus 5 halves, a plus 5 halves, and 17 halves. Not a good choice, maybe. In the second row, you could divide by 3, but then you get a 1 there, but then you'd have a minus 2/3, a 1, and 11/3. A little bit better than the previous one, but still not great. The third one wouldn't be too bad. Divided by minus 3, that would be a 1, minus 1, and a positive 16, a 0, and positive 16/3. So of all your divisions, that would be the division I'd go for if I went for it. But your suggestion of subtracting row 1 from row 2 might be the best case, okay? And then moving that up and making that your row 1. So we won't carry it any further, but that is a good choice. You can do that here in the early stages because you're not going to mess anything else up. Once you get 1s and 0s in place, when you start doing that kind of stuff, you're going to screw them up, okay? So you can't do that later. First step, yes, you can do it. So what it says here, sometimes judiciously choosing the order in which you apply the elementary row operations enables you to avoid fractions. And sure enough, that choice did it, okay? Now, here's a completely different problem, though parts of it look somewhat similar, but it's different, so I'm going to erase everything. All right. 2x1 plus 3x2 plus 5x3 is equal to 0, minus 5x1 plus 6x2 minus 17x3 is equal to 0. And 7x1 minus 4x2 plus 3x3 is equal to 0. Now here they make a sort of a strange request. Without doing any row operations, explain why the following, that system right there of linear equations is consistent. Without changing it to a matrix, without doing any row operations, can you convince me that is a consistent system?
All variables could be equal to 0.
Okay, yes. 0, 0, 0 makes every one of those true, right? Yeah, of course. Now, what we call this system is a homogeneous system. All the constants are 0. Anytime you have that, you know you have at least one solution, and what they call the trivial solution. 0, 0, 0, because that's going to make everything 0. Now, you may have infinite number of other solutions, or that may be your only solution, okay? But you know it's going to be consistent. Consistent means you have at least one solution. You may have many, but yeah, okay? Now, all right, I'm going to do something because they set it up for me this way. I'm going to do something a bit strange, okay? I'm going to add a 2x4 to the top one, subtract the 3x4 from the second one, and add a 13x4 to the next one. And then set all these equal to 0. Okay? Now, this system, by the way, has more variables than it does equations. Now, it doesn't have to be homogeneous, but it happens to be homogeneous. But anytime you have more variables than you do equations, you've got to have infinite number of solutions. No way around that. Okay, if you have more variables than equations, you're going to have an infinite number of solutions. Now, I say that, and then I want to catch myself. Yeah, especially if it's homogeneous. Okay. I guess if you had numbers out there, you could do elementary row operations and then wind up with an impossible situation. Well, I don't even think you can. I don't think it's possible to do it. So, but anyway, in this case, you will have an infinite number of solutions. Okay. So, let's do example 8. Okay. Whoa! Seems like we're going backwards here, folks, doesn't it? Solve this system of linear equations. 2x1 plus 4. Oh, no, I'm sorry, I misread it. 4. Well, I can't read my writing. There's my plus sign. Here's my 4. 4x2 minus 2x3 is equal to 0. And 3x1 plus 5x2 is equal to 1. All right. It says solve that system of linear equations. What would be your first step? Write the matrix. Now I'm going to be real lazy like I did before and do it this way. Is that okay? Just wipe out my x1s, wipe out my x2s, wipe out my x3, and wipe out my equal signs. Okay. That is really being lazy. I don't think I've ever been this lazy before. Okay. My old age, I guess. Now, what do you want to happen first? Now, notice here, this is something similar to what we had before, but it's not homogeneous. It's not all zeros. Would your guess be that you're going to have an infinite number of solutions? You got more equations than you do unknowns. Unless by chance this is an impossible system, it should be infinite number. But let's see. What do you want to happen first? Okay, how do you make that happen? Divide by 2. I think that's the best way to do it. So let's do row 1 divided by 2. Okay, I'll write this one out because it's pretty short. What would that be? You tell me. 1, 2, -1, 0. Okay, that was easy enough. And then we'll write down 3, 5. Oh, I should have put a 0 in here. 0, 1. Okay. What do we want to happen next? The 3 becomes a 0, and how do we make that happen? row 2 minus 3 times row 1. Okay? All right. So we're using row 1, so that's going to be 1, 2, minus 1, 0. And what does your new row 2 become? 0. Negative 1. 3. Is that what you said? 1. Okay. Now what's the next thing you want to happen? Okay, make the negative 1 a 1. Is that what you mean? Yeah. That's going to be real easy to do, isn't it? Plus, minus, minus. Okay? Done? Okay. What we did there was minus row 2 is the new row 2. Okay, that's all we did. Okay. Next, make a 0 above. How do you make that happen? Row 1 minus 2, row 2. Okay. And we're using row 2, so write it down 0, 1, negative 3, negative 1. And what's your new row 1? 1, 0, 5, 2. Is that what you said? I can't hear well. Okay. 2. Okay. And guess what? It's all we can do. Okay? Now, remember, this stood for since I roasted it, okay? This stands for X1s, this was your X2s, this was your X3s, and these were your constants, okay? So what this says is X1 plus 5X3 is equal to 2, right? And this says X2 minus 3X3 is equal to negative 1. Well, it's pretty obvious here. We know something about X1 and something about X2. We have no real knowledge of X3. So let that be a parameter. And do you remember what I said the favorite parameter usually was? I don't know why, but it's t. Okay? So let X3 equal t. So that then tells us X1 plus 5t is equal to 2, and X2 minus 3t is equal to negative 1. Okay? Well, let's solve for X1. That would be X1 is equal to 2 minus 5t. X2 is equal to 3t minus 1. And, of course, X3 is equal to t. That was what we started with. So now our solution would be 2 minus, I can't write. Yuck, it didn't take. Okay. 2 minus 5t, 3t minus 1t. And then you can come up with an infinite number of solutions. Give me a t. 0. So what would that solution be? 2 minus 1, 0. Give me another t. 1. This would be negative 3, 2, 1. Any t you want to choose, you can come up with another infinite number of solutions. What we call t is your parameter. That's the variable that has no leading one. Those will always be a parameter. You could have 2, 3, or 4 of them. So usually if there's 2, they do s and t, okay? If they have 3, what do they use? S, T, and U maybe. I don't know. They just pick letters. Usually not X and Y, obviously, okay? But pick letters and let those be your parameters, okay? And unfortunately, I believe we have run out of time. Let's just make sure we got the same thing they did. 2 minus 5t minus 1 plus 3t. It doesn't matter which way you do it in t. Got it, okay? So we'll start next time with homogeneous systems, which we actually hit in our discovery section. We'll start there next time. Let me give you a few homework exercises. I know you wouldn't want to leave home without them. Okay, and basically we just are almost at the end of the section. So do any of the odds 1 through 5. And by the way, the answers to the odd numbers are in the back. And also, I think I told you before, see calcchat.com for worked out solutions to the odd number exercises. That's why I give you the odd numbers. First, check your answers. If you don't get the right answer, see if you can figure it out. If you can't possibly figure it out, or it's just bogging you down too much, go to calcchat.com, free website, and you can see the worked out solutions there. If you don't know why they did certain steps, then bring it to class and we'll discuss it. So any of the odds 1 through 5, either 7 or 9 or both, any of the odds 11 through 17, any of the odds 19 to 23, any of the odds 25 to 29, 25 to 37, do 39. Now that's a pretty hefty problem. It says use a software program or a graphing utility to do that. If you got one handy, use it. If not, work with it a little while, and if it gets way too tedious, then quit. Just see what it's like to deal with. And then let's stop there because that's when you get into homogeneous systems. So we'll pick up from there next time. All right. Any questions? Good deal. Have a good weekend. Of course, what's going to make it a good weekend? Doing linear algebra problems, of course, okay? And maybe a few differential equations, right? Okay, so have a good weekend, and we'll see you. We will not see you on Tuesday, okay? Remember, no class, not this class. We'll be here for the 8 o'clock class, okay? But no 10 o'clock class, because I'll be at the doctor's office. And I do have a treatment on Friday, but Friday of next week is no longer in class. So, no longer school. We'll see what I'm like next Tuesday. All right. See you Thursday.